So in the last class, we were dealing about the kernel. That is one of the basic or fundamental structure of an operating system. So in the case of kernel, it offers the following services. We have just mentioned about the services, and out of these services, process management, memory management, and device management. These three details or these three management strategies will be discussed in detail. The first one was related to process management, and we started off with process creation. So we have seen an example as the case of our mobile phone. When we turn on the mobile phone, the first process that we initiate is the display process. So similar to that, we will be dealing with the process creation at first. The first step is that at the reset of the processor in a computer system, an operating system is initialized first, enabling the use of operating system functions. So the first thing that happens is that when we reset the processor in a system, the first thing that is happening is that the operating system is initialized first, enabling the use of OS functions. So it enables the use of OS functions so that this OS function includes the function for creating a process also. You will be having a function like OS task create. This is a function for creating a particular task or process. Similar to that, the first process when we reset the processor is that it enables the use of operating system functions. Okay, so which includes the function to create the processes also. So by using that function, we will start or create a process which can be called the initial process. So in the case of our mobile phone, it will be the display process. That will be the initial process that we create. And then OS to be started, and that calls the initial process to run. When the initial process runs, it creates subsequent processes. You can consider the case, when you initiate the display process, that will be the parent process to display. And then inside that, you will be having various things like you need to display the time, you need to display the date, battery, signal. So all these will be sub processes. So after creating the initial process, that is the main process, the sub processes will be created in a hierarchical manner. That is the first process, that will be the parent process, and then you will be having the child processes. Then what is actually creation of a process? It means specifying the resources for the process and address space. Two major things have to be specified. Mere process is not enough. We need to provide resources for the process. At the same time, we need to provide memory space also. For the execution, we require devices or we require resources. Code എന്ന് പറയുന്നതാണ് process എന്ന് പറയുന്നത്. It is just a part of the code. So that doesn't serve our function. We need resources for performing that task. Along with that, we need memory space. These two will be specified during the creation of the process. And also another thing is that all the informations regarding the process will be placed in a block called process control block that we have already seen while discussing about the process. So during the process creation, three things are happening. One is that specifying the resources for the process, then allocating the address spaces, and then providing all the informations in a process control block or PC. Then this will be very essential while you are performing a context switching. That is when you are shifting from one process to another process. I have already mentioned that the processor will not be functioning on a single process all the time. It will be switching in between. So during this switching process, the values in PCB is very essential. So that's why we are copying all the informations regarding the processor, regarding the process within the PCB or process control block. And this is particularly called the process descriptor. Okay, PCB is called the process descriptor. All ID details, and then all such details, all the context details, etc., will be stored in the process control block. Now we will see what all are the things that are present in the process control block. So you just remember this thing from process creation part. Initially, we will reset the processor. At that time, OS will initialize. First process that happens, or first step that happens, is OS initialization, enabling the use of operating system functions. Operating system function also includes the operating system function for creating a process. OS task create, അല്ലെങ്കിൽ OS create. Some process has to be created. അതിനുള്ള ഫംഗ്ഷനും ഓപ്പറേറ്റിംഗ് സിസ്റ്റത്തിലുണ്ട്. That also will be enabled at the time of operating system initialization. So after that, by using that function, we will be enabling the, we will be creating a process, and that process will be run by the operating system. And during that run, the subsequent processes are also being created in a hierarchical manner. And what happens during a process creation? Three major things, that is specifying the resources, address spaces, and placing the information in PCB. PCB is a process descriptor used by process manager. So all these management techniques, that is process management, memory management, and device management, all these management strategies will be having separate managers. That is, process manager will be there, device manager will be there, memory manager will be there. So here the process manager allocates a PCB when it creates the process and later manages it. So it is it is a function of process manager to allocate the PCB, that is to fill the PCB and to manage it later. That is, the values have been changed later during the time of execution. Now let's see what all are the contents present in the process control block. Okay, the first thing is that context. Context is a very important term, because context includes the, I'm telling about the PCB, the contents of PCB, that is process control block. The first thing is context. The context actually includes the processor status word, then program counter, then stack pointer, and all the CPU register values at the instant of last instruction execution. That is, during the execution of a particular instruction, all the details like processor status word, then program counter, then stack pointer, then similar to that, all the CPU register values at the time of execution of last instruction will be stored in the context, will be actually the context. Context in the processor status word will be there, then program counter value, stack pointer value, and other CPU register values at the instant of last instruction execution. Okay, that will be the content of context. Then we have the process stack pointer, then the current state of the process, that is whether the process is now in the created state, activated state, or spawn state. Spawn state is actually create and activate. Spawn, create and activate state is called spawn state. Then is it in the block state? So the different states of a process, and that will also be that value, that status will also be present in the process control block. Then addresses that are allocated and that are presently in use. So when a process is created, we have already mentioned that during the creation of a process, what are the three different things happening? One is that specify the resources that are to be used by the process. Another is that assign memory space, right? So we will be assigning a memory space to the process. So within that memory space, addresses that are allocated and that are presently in use, that will also be present. That is also a content of PCB. So PCB എന്ന് പറയുന്ന പ്രോസസ് കൺട്രോൾ ബ്ലോക്കിൽ ഉള്ള കാര്യങ്ങളാണ് പറയുന്നത്. കോണ്ടെക്സ്റ്റ്, process stack pointer, then current state of the process, whether it is created state or activated state, spawn state, or is it in running state or block state. Then addresses that are allocated and that are presently in use. Then pointer for the parent process and pointer to a list of child process. This will be in a hierarchical manner. Child process will be having a lower hierarchy when compared to the parent process. Then pointer to a list of resources which are usable only once. Okay, a list of resources which can be used only once. Pointer means address. This PCB will actually be containing the address of a list of resources which can be used only once. Then address of a list of resources which can be used more than once. Then pointer to queue of messages, pointer to access permission descriptor, and finally processor ID. Process ID. You will be having plenty of process and you need to distinguish between these processes. So each process will be given a process ID, and that will also be present in the process control block. So these are the contents of process control block. Context, process stack pointer, then current state of the process, addresses that are allocated and presently in use, pointer to the parent process, pointer to the list of child processes, then pointer to a list of resources which are used only once, then pointer to a list of resources which are usable more than once, pointer to queue of messages, pointer to access permission descriptor, and ID, that is the process ID, PID, that is process ID. And now we have the management of created process. One second. Yes. Next is the management of created process. So the first part was process creation. Now the management of created process. So here comes the role of process manager. Process manager is a unit of operating system that is the entity responsible for controlling the process execution. Process management enables the process creation, activation, running, blocking, resumption, deactivation, and deletion. So these all are the, and we have already mentioned, we have the process management right from process creation to deletion. Adinadakkulla steps are activation, running, blocking, then resumption of the, that is resuming the blocked process. That is actually resumption. We can block the process, we can resume the process, then deactivation and deletion. So all these actions or functions have been performed by the process management. Then the functions of process manager makes it feasible to let for a process to sequentially execute or block when needing a resource and to resume when it becomes available. That is for the sequential execution of process. Also providing resources. Processes or all the processes require resources, and allocation of these resources is also done by the process manager. Then implements the logical link to the resource manager for resource management. That is already mentioned. That is resource management is another function of process manager. Then allows specific resources sharing between specified processes only. Certain resources need to be shared between certain processes only. So that is also done by the process manager. That is specific resources shared between specified processes only. Then fourth one allocates the resources as per the resource allocation mechanism of the system. And fifth one manages the processes and resources of the given system. As a whole, you can say that the ultimate function of process manager is resource allocation. That is how the processes have been provided with the resources, how these resources have been allocated to the processes. That's actually the function of process manager. And the second thing that I have mentioned, that three things that we will deal in detail are process management, memory management, and device management. Out of that, the second point is memory management. So it was also already mentioned that is while creating a process, we need to allocate memory space also. Okay, so when a process is created, the memory manager allocates the memory addresses or blocks to it by mapping the process address space. So the space, that is the memory space that is allocated to a particular process, is actually called the process address space. Okay, we'll be having multiple threads within a process. ഒരു പ്രോസസ്സിനകത്ത് multiple threads ഉണ്ടാവും. So all those threads will be sharing the same memory space of the process. Okay, the threads will be using the same memory space which is allocated to a particular process. Threads are coming under a particular process. Threads will be coming under a particular process, and these threads will be using the process address space. That is the address space allocated to the process. Then regarding the memory manager, that is similar to that of a process manager. In case of memory manager, it has to be secure, robust, and well protected. That is, it should be efficient, it should be secured. These are the two criteria. It should be efficient and secure. Secure in the sense, it should be protected. The memory space, we need certain protections in memory space. We have already mentioned about the two modes in which the processor can work. Like we have mentioned about the two modes. Which are the two modes? Which are the two modes in which processor performs in the case of an operating system? And while considering an operating system, which are the two different modes? ഏതൊക്കെയാണ് രണ്ട് modes? User mode and supervisor mode. Okay, these are the two modes, but you will easily understand that the supervisor mode is actually being used by the kernel. Kernel will be activated in the supervisor mode. That is, the user will not be able to access the kernel memory space. We'll be having, from that itself, it's clear that we'll be having two memory spaces. We'll be having the kernel memory space as well as the user memory space. So the user will not be having any access to the the kernel memory space. അല്ലെ, നമുക്ക് സിസ്റ്റം ഫങ്ഷൻസ് എഡിറ്റ് ചെയ്യാനുള്ള ഓപ്ഷൻ നമുക്കില്ല. വി കനോട്ട് എഡിറ്റ് ദ സിസ്റ്റം ഫങ്ഷൻസ് ഓർ ദ സിസ്റ്റം പ്രോഗ്രാംസ്. So for that, what should we do? We need to secure that memory area, right? We need to secure that സൂപ്പർവൈസർ അല്ലെങ്കിൽ സൂപ്പർവൈസർ മോഡിൽ സിസ്റ്റം വർക്ക് ചെയ്യുന്നത് കേർണൽ മോഡിലാണ്, അല്ലെങ്കിൽ ഓപ്പറേറ്റിംഗ് സിസ്റ്റം ആണ് സൂപ്പർവൈസർ മോഡിൽ വർക്ക് ചെയ്യുന്നത്. So that memory space has to be protected from the application or from the user, and that's the term we call secure. The memory space has to be secured, should be protected. Also, there should not be any memory leaks and stack overflows. Memory leaks means, suppose we are trying to write in a memory block that is not allocated to a process. When a process is created, a memory space is also allocated to the process, right? When we are creating a process, a memory space is also allocated to the process. If we are trying to write to a memory space that is not provided to a particular process, then an error can occur. So this should be prevented, and all these things, that is memory, that is actually what we mean by memory leak. That is attempt to write in the memory block not allocated to a process or data structure. Okay, we'll be having many address blocks. If we are trying to access a block that is not assigned to that particular process, then it is called memory leak. And stack overflow is similar to that. Stack overflow means stack exceeding the allocated memory blocks. Whenever we are trying to access a memory block that is out of our allocation, out of the allocation of the process, processനെ allocate ചെയ്തതിന് അപ്പുറത്തേക്ക് നമ്മൾ ഒരു മെമ്മറി ആക്സസ് ചെയ്യാൻ നോക്കുകയാണെങ്കിൽ, that is actually called memory leak and stack overflow. So this also has to be monitored by the memory manager. Two major things: no memory leaks and no stack overflows. These two things have to be maintained or considered by the memory manager. Then these are the different memory managing strategy for a system, similar to that of process management. Normal process manager, we have seen different steps, right? You remember the different steps, right? From process creation and process management, we have seen the different steps. Similar to that, we are having a strategy in the case of memory management also. So these are the different terms that are included. One second. Okay. Okay, these are the different memory strategy for a system, memory managing strategy for a system. So the first one is fixed block allocation. Fixed block, from that name itself, you will be having a clear idea. I mean, first of all, I will just read the different strategies. Fixed block allocation, then you have dynamic block allocation, then dynamic page allocation, dynamic data memory allocation, multi-processor memory allocation, memory protection to OS functions, memory protection among tasks. So from the name itself, you will be getting some idea regarding certain features. Clear out. And we start with fixed block allocation. So in the case of fixed block allocation, the entire memory space will be divided into blocks. Block in the sense we'll be having different units like 64K or 256K. In that basis, the entire memory blocks will be divided into entire memory space will be divided into blocks. And with the processes having small address space, we'll be having some processes with small address space, and we'll be having some processes with bigger address space. Okay, you'll be having processes with smaller address space and processes with bigger address space. So the processes which are having smaller address space will be provided lesser number of blocks. So initially the entire memory space will be divided into fixed blocks. Okay, entire memory space will be divided into blocks, and now we need to assign these blocks to the processes. So certain processes require small address space. So for that processes we will be allocating lesser number of blocks, memory blocks, and certain processes which require bigger address space will be allocated with larger number of blocks. It depends upon the number of blocks. That is how we are assigning the number of blocks. We are initially dividing the entire memory space into number of blocks. We are dividing that. And now we need to assign a particular number of blocks to different processes. So on this basis, on the basis of requirement of address space, we will be allocating larger number and lesser number of blocks to different processes. Coming to the dynamic block allocation, it is also similar to that of fixed block, but the blocks have been allocated during the computation process. Okay, in the case of fixed block allocation, we are initially allocating, or at first itself we are allocating the blocks to the processes. But in case of dynamic block allocation, the variable size blocks, here actually variable size block, it's not fixed size blocks. In dynamic block allocation, variable size blocks will be allocated to the process at the computation phase or during the computation phase. Fixed block in the case, initially then we blocks in assign the process. But in case of dynamic block allocation, we are allocating that to the process during the computation phase or during the execution time. Dynamic page allocation. Here actually the fixed sized blocks are actually called pages. Dynamic page allocation case, the fixed sized blocks in the sense the memory space, memory space in a divide blocks. We are having fixed size blocks. In case of fixed size blocks are actually called the pages, and these fixed size blocks are dynamically allocated to the process. Okay, in this case, fixed blocks in the case it is initially allocated. Creation time is allocated. Dynamic blocks in the case, variable size blocks are allocated to the process during the runtime. Here, fixed size blocks are called page, and they are allocated during the runtime. And here, dynamic data memory allocation. That is the memory allocated dynamically to the different data structures. Data structures like queues, mailboxes, stacks, etc. These are all data structures. And we are allocating dynamic data memory allocation runtime. We will be allocating memory to the data structures. Okay. Dynamic data memory allocation is allocation of memory to data structures. Data structures are queues, then stacks, etc. These are the data structures. And we will be allocating memory to these data structures during the runtime. Then multi-processor memory allocation, obviously, it deals with how the memory is being shared between two or more processors. If you're having two or more processors within the system, how the memory is being shared between these processes. All these things are managed by the memory manager. Then memory protection to OS function. This I have already mentioned. Certain functions or operating system functions has to be protected from other processes. No process should be allowed to enter into the protected memory space. That is the OS or kernel memory space. All the processes, only the kernel or operating system will be having the capability to work in the protected memory space. ഓപ്പറേറ്റിംഗ് സിസ്റ്റത്തിന് വേണ്ടി അലോക്കേറ്റ് ചെയ്തിരിക്കുന്ന മെമ്മറി സ്പേസ്, ദാറ്റ് ഈസ് എ പ്രൊട്ടക്റ്റഡ് മെമ്മറി സ്പേസ്, അതിൽ നമുക്ക് യൂസർ പ്രോസസ്സസ് ഒന്നും അതിലേക്ക് എൻ്റർ ചെയ്യാൻ പാടില്ല. ആൻഡ് ദാറ്റ് പ്രൊട്ടക്ഷൻ ഈസ് ഓൾസോ എൻഷുർഡ് ബൈ ദ മെമ്മറി മാനേജിംഗ് സിസ്റ്റം. Then memory protection among tasks. I have already mentioned a particular process is assigned a particular memory space. So no other process should come into its place. വേറൊരു പ്രോസസ്സും അതിന്റെ മെമ്മറി സ്പേസിലേക്കും വരാൻ പാടില്ല. That's actually what we mean by memory protection among tasks. The different tasks will be allocated different memory spaces, and it should be exclusive. They should not be coming into another process's memory space. That protection also has to be ensured. So memory protection to OS functions, also memory protection among tasks. Within the task, it's also we need to have memory protection. Then coming to memory manager, different functions like use of memory address space by a process, specific mechanisms to share the memory space, specific mechanism to restrict sharing of a given memory space, optimization of access periods of a memory by using a hierarchy of memory. And this you will be aware, like cache, different hierarchy of memories like caches, primary, external, and optical memories. And here you have the order of access periods also. That is the time taken to access the different memories like caches, primary, external, and then optical. And this is the increasing order. Memory manager, where in the case of process manager, in the case, its main function was to allocate resource to a particular process. Here, it is allocating memory address space to a particular process. How that memory space is been allocated. Then coming to the third point, that is device management. Device management, I think you might have seen about the device management. You can see the device manager in the system also, right? In computers also you can see the device managers. See, in your system also you can see the device manager. Device manager is actually dealing with the entire hardware devices that are connected to the system. And that is also, management of that is also a part of kernel, or it's a function of kernel. You can see the different hardware devices that are connected to the system. You will be having the USB, that is USB, then the audio, cameras, then disk drives, then including the monitors, mouse, keyboards, everything will be controlled or managed by the device manager. You can see that. So this is also a function of kernel or operating system, that is dealing with the device drivers and to manage the devices. That is communication between devices. So the system has to communicate with these devices, right? Even when we are using the keyboard, the processor will have to communicate with the keyboard. When we are using a mouse, it has to communicate with the mouse. So this is actually the part, that is device management is actually the part which performs that operation. That is communication between the various hardware devices connected to the system. And that is also a function of kernel. So device management, software that manages the device drivers of each device, provides and executes the modules for managing the devices and device ISRs, effectively operates and adopts appropriate strategy for obtaining optimal performance of the devices, coordinates between application process, driver, and device controller. So these are the main functions. You can read this. No much explanation is required in this video. Our primary concern is regarding the different functions we will deal. First of all, we need to see in the device manager, the 3 different types of device drivers is important that we have already learned. That is programmed IO, how the communication is taking place. The first thing is programmed IO, then interrupt driven IO, and then DMA operation. This we have already learned in the previous modules. The 3 different types of device drivers based on how input output data is being transferred, how the data transfer takes place. On that basis, we have 3 different types: programmed IOs, interrupt driven IOs, and DMA. So in device drivers, you need to study this. Then device manager functions. This is also important. These are the functions of device managers. So first one is device detection and adhesion. That is the first function of device manager. That is, this actually provides code. Code means program, provides codes for detecting the presence of a particular device, then adding these devices for the use of operating system. At first, the device has to be detected. So device management function first one was the device detection and adhesion. So e part certain codes will be provided for detecting a device and for adding the device to the operating system. Okay, for detecting the device, certain codes will be there. Certain codes will be there for adding them for the use of operating system. Then second is device deletion. First one is device detection and adhesion. Second is device deletion. Here it is actually providing codes for denying a particular device resource. That is, we are not using a particular device, then we need to deny that resource. For that, we will be having certain codes. Codes mean programs, and that is actually coming under device deletion. In order to code for detecting the device and for adding the device to the operating system. Then device deletion is actually denying the device resources. If you are not requiring that particular device, we need to deny that resource. And that is those particular codes will be coming as part of device deletion. Then device allocation and registration. That is, all these devices, normally connected to all devices, there should be some sort of address spaces, right? There should be some address spaces for all the devices that we are using or that we are connecting to a particular system. This allocation process, that is allocation of addresses to the various devices. Allocation of addresses to various devices is also a function of device manager. Allocation of addresses to the various devices. And also we should ensure that no 2 devices are having the same address. That should also be seen. That is, there should not be any collision. All the devices should be provided with different addresses. So first, device detection and adhesion, then device deletion. The third one is device allocation and registration, where we will be allocating addresses, that is either memory or register addresses, for the various devices that we connect. Also should ensure that there should not be any collision between the address allocation. Then once it is allocated, the opposite of that is detaching and deregistration. Detaching in the sense we are removing that allocated address. We are allocating address in this phase, and the next phase is actually for detaching and deregistration. That is, detaches and deregisters the port. നമ്മൾ ഈ ഡിവൈസസ് നമ്മൾ സിസ്റ്റത്തിലേക്ക് കണക്ട് ചെയ്യുന്നത് ത്രൂ എ പോർട്ടാണ്. ആ പോർട്ടിന് ഒരു അഡ്രസ് പ്രൊവൈഡ് ചെയ്യുക എന്നുള്ളതാണ് ഡിവൈസ് അലോക്കേഷൻ ആൻഡ് രജിസ്ട്രേഷൻ എന്ന് പറയുന്നത്. At the same time, if you are detaching the address space or detaching or deregistering the address space, that is coming under this phase. Then restricting device to a specific process. That if a particular device is meant only for a particular process, that can also be done. That is also done with the help of device manager. That is, we are restricting the operation of a particular device to a particular process only at a particular instant. ഒരു particular time ഒരു ഡിവൈസ് ഒരു പ്രോസസ്സിന് വേണ്ടി മാത്രം നമ്മൾ റെസ്ട്രിക്ട് ചെയ്യുകയാണെങ്കിൽ that also is a function of device manager. That is, we can restrict a device access to just one process at one instance. Then in contradiction to that, we have device sharing also. We can share a particular device among multiple processes. Here actually we have restricted device to a specific process. Here actually we can perform device sharing. That is, we can share the devices between different processes. That is, this phase actually permits sharing of devices between the different processes. But make sure that only one process is accessing a device at a time. At a time, only one process will be accessing, but that device will be shared to multiple processes. Then device control. Device control in the sense we can control a particular device from a remote server. It will not be through that particular system itself. That is, suppose we are having a server client approach, and from the server we are controlling the client. So in that sense, that also is a function that is provided by the device manager. That is, we are controlling a device from a remote server. You cannot like that. Device control means that is controlling a particular device from a remote server. So these are the main functions of device management. So now we can mark your attendance.